great. Okay, I think we passed the threshold. Okay, Assalamu alaikum wa rahmatullahi wa barakatuh all. Thank you all for joining to this webinar with Dr. Hussam al-Sharif. And this is part of the webinars with the Interdisciplinary Center for Hydrogen and Energy Storage. I'm the Atif Zahrani. I'm the Energy Storage Program Coordinator, and I'm very happy, very honored to introduce to you our speaker, Dr. Hussam al-Sharif. Dr. Hussam al-Sharif is a professor of material science and engineering at King Abdullah University of Science and Technology. He obtained his PhD at North Carolina State University in 1996, followed by a postdoctoral fellowship at the Sandia National Laboratory, USA. He then embarked on a 10-year career in semiconductor industry, holding positions at Micron Technology at Texas Instruments. Then he worked on developing new materials and processes for the microelectronic industries. In 2009, he joined KAUST, where he initiated an active research group focusing on the development of nanomaterials for electronics, sensors, and energy storage devices. He has won the UNDP Undergraduate Fellowship, Seth Bragg Physics Award, North Carolina Dean's Fellowship, U.S. Department of Education Electronic Materials Fellowship, Sandia National Laboratory Postdoctoral Fellowship in 1996, the CMATIC Corporate Excellence Award in 2006, 2 Dow Sustainability Award 2011 and 2014, and A.H. Sherman Award for Excellence in Energy Research in 2016, KAUST Inaugural Distinguished Teaching Award 2018, and the Kuwait Prize for Sustainable and Clean Technologies in 2018. He is a fellow of the American Physical Society, Royal Society of Chemistry, and the Institute of Materials, Minerals, and Mining, and the IEEE Distinguished Lecturer in Nanotechnology. He is a Clarivate Analytics Web of Science highly cited research in material science, mashallah, 2019-2021. He's the author of 510 journal articles. He has over 75 issued and pending patents. He serves on the editorial board of several international journals. Please help me welcome Dr. Hussam al-Sharif. Dr. Hussam al-Sharif, the floor is yours, and we are very excited to hear your presentation.
Thank you, Dr. Atif, very much for this nice introduction, and also thank you and Dr. Zain for the kind invitation. I'm really delighted to talk in your seminar series. So, as Dr. Atif said to listeners, I come from the Material Science and Engineering program at KAUST. I actually joined KAUST from the beginning, 2009. We work in the area of energy storage. So today I'm going to talk about rechargeable zinc-ion batteries. Just in case we run out of time, I want to thank many people, people in my group, those who are here and those who are left, for their contributions. Several professors at KAUST, especially Professor Cavallo and Udo, who done a lot of computational work with us, former students and postdocs of mine, and also Energy Initiative at KSU and Energy Materials Initiative at KAU, Professor Mushtaq Dar and Professor Noura Al-Habshi. So with that introduction, let me just say a couple of slides about renewable energy. As many of you know, we are going through a transition from fossil fuels to renewable energy, and one characteristic of a lot of these renewable energy systems is that they are intermittent by nature. So, for example, at night, we do not have solar power. But the load in our homes, what we need to run our appliances is constant. So there's a need to be able to store energy when the solar power or the wind is not available. We need that stored energy to be able to continue to provide the constant power output for our needs. So the way we store energy, there are many energy technologies, and they span different approaches. You can store potential energy, kinetic energy, electrochemical energy, chemical energy, and thermal energy. Just a fact for you, this potential energy storage, the most basic and simplest way, they actually, when they have excess electricity, they pump water to a top of a hill or a mountain, a small mountain, and then when they need that energy, they let the water come down to run a generator. In the US, this simple and basic, it's not high-tech storage technology, accounts for almost 95% of all the energy stored in the USA. So there's actually a lot of locked-in potential. And I don't have time to go through how all of these technologies work, but I do want to say that I am interested in electrochemical energy storage. This is basically batteries and electrochemical capacitors, let's say, because they are extremely compact. They have no moving parts, and they basically require considerably less maintenance to keep them running. So in fact, if you look at the projections for the size of the battery market, it's huge. There are one of many websites that talk about energy, and basically they predict that the amount of money that will be invested in battery storage by 2050 will be something like $550 billion. So you can see there's a huge potential in this market that we should capitalize on. Of course, the elephant in the room when you talk about lithium-ion batteries, is the lithium-ion battery. The reason is that this is the most successful battery technology. It has entered our daily life in many ways. Our portable electronics, transportation, home-based storage, and now grid-level storage, all is based on lithium. The truth, this is a very successful technology today, and the truth is that the price has been coming down for the last 10 years. It's like just above $100 per kilowatt hour now. But many people think this is really near the bottom. And in a way, in the future, when we become a victim of our own success, the more cars we make, the more lithium we need. But we know that the supply of lithium is actually finite. If you look at this chart here, which compares the fraction of the elements in the earth crust, you will see this is a log chart, log scale on the y-axis. You will see that lithium is orders of magnitude, for example, lower than sodium. So as we make more cars, as we deploy more lithium-ion batteries, this is going to become an issue, and this will drive up the cost. Also, on top of this, if you look at this world map, actually the lithium reserves are placed, they're not uniformly distributed in the world, and that creates an issue because everybody needs lithium. On top of that, we have safety problems. Many of you are aware of incidents involving lithium-ion batteries, and this also puts stringent requirements on the fabrication, which adds to cost. So the question is that what will we do when the time comes and the lithium supplies don't become enough to meet our demand? That is really the crux of the whole presentation. And there is actually a simple way to look at this. One strategy that people are doing is that to try to have an iterative development, basically increase the energy density beyond, let's say, 300 watt-hour per kilogram for portables and electric vehicles. And this goal actually capitalizes mostly on lithium-based technologies. For example, designing better cathodes, introducing silicon into the graphite to increase the capacity of the anode, solid-state batteries that use lithium metal and therefore can capitalize on its higher energy density, lithium sulfur, lithium metal batteries. All of these rely on lithium. But lithium is expected to be expensive today, even for grid storage. It's expected to become more expensive. So another way, which focuses on developing a lower cost solutions, this is for grid storage, okay, where we're gonna really replace all these hydroelectric stations that I talked about. Then you need a cheaper solution. These cheaper solutions that people are looking at involve sodium ion because it's more abundant, potassium, and also multi-level storage, using multivalent storage, using ions like zinc, like magnesium, like aluminum. Here, multiple electrons are involved in the redox reaction, which of course increases the energy density. Flow batteries, sodium sulfur, at 300 degrees C, even at room temperature, people are interested. So this is really the deal. Some of the technologies for the near future that we talk about, this is for option number one, the blue here, includes increasing the capacity of the cathodes, the solid silicon graphite alloy, solid state battery, and then the lithium sulfur or lithium oxygen. That's the landscape of what people are working on next. But if you look further out, and especially focus on grid energy storage, we may need different technologies. And this is where the zinc ion batteries come in. So why are we interested in zinc ion batteries? Okay. There are, theoretically speaking, there are several reasons why this zinc ion technology may be promising. Number one, zinc is safe. You can handle it in the air. You can, process it. It's not prone to the fires that lithium is. and it's environmentally friendly. It is significantly more abundant than lithium. If you look at the cost, for example, a kilogram of zinc is $2, a kilogram of lithium is $20. So this is an order of magnitude higher cost. And because it's divalent, means it is possible that multiple electrons can be transferred in the redox reaction. This results in higher capacity. If you look at the chart here on the bottom, you see the capacity, volumetric capacity is 5,800 milliamp hour per centimeter cube. And the gravimetric capacity is lower, but still high. This is because the zinc is dense, it has higher density than the other mobile ions. So it ends up with a smaller gravimetric energy density, but it's still very respectable. The ionic radius, if you look at the top graph, it's comparable to lithium. Although we should qualify the statement, in the end, it's not only the ionic radius, it's really the hydrated ion that matters, but nonetheless, it doesn't have too big of a radius to start with. It has a suitable redox potential. You see here, compared to the other ion in the red curve, it is stable in aqueous electrolyte, and also that makes it maybe less prone to hydrogen evolution in principle. So these are the attractive features of this technology and why we became interested in it. And by the way, the zinc ion battery is an old technology, just to be sure. It actually started in 1800. This is the Volta pile, which uses zinc and copper connected in series. In 1882, the zinc manganese oxide battery was invented. Believe it or not, this is the primary battery that is gets discharged once and then you throw it away. Believe it or not, this battery is actually commercialized and we are still using it today. A lot of the AA and AAA batteries we use are based on this technology. It's a $10 billion a year technology. In 1899, the zinc nickel battery was invented, and in 1941, zinc silver oxide. All of these are primary batteries, means you discharge once. So then in the 80s, people started working on rechargeable batteries, zinc ion batteries. So these are like the lithium ion battery, rocking chair battery. And the main battery that people started with was a zinc manganese oxide using zinc sulfate electrolyte. That battery had a lot of problems. I will explain in a few minutes. So people started to actually play around to try to improve the performance by using dual ion electrolyte, ionic liquid electrolyte, water and salt electrolyte, organic electrolyte, or they started to play with the cathode and anode construction to try to mitigate some side reactions. So if you look at the number of papers on this technology, in the last few years, it is going up astronomically. Huge increase in the last couple of years in people looking at zinc ion batteries. So this is the fundamental structure of the zinc ion battery, the rechargeable battery. It looks a lot like the lithium ion battery. You have an anode, which is often zinc. So technically, we should call this a zinc metal battery, but people are calling it zinc ion, zinc metal. But your anode here is metal. If this was lithium ion battery, we would say lithium metal battery, use zinc anode. So I use them interchangeably, forgive me. And then here's your cathode. It could be an oxide, it could be a 2D material, and you have a separator in between. Okay, so what are the issues with the zinc ion batteries? Many. Okay, there are issues at the cathode. For example, cathode dissolution. Okay, manganese oxide is notorious for this problem. Because zinc, as I will show, even though the ion itself is small, it is hydrated by 6 water molecules. It actually becomes large. So when you intercalate it in the cathode, you cause structural instability in the cathode, and it doesn't last very long. There's also surface reactions. At the anode, it's even worse. You have dendrites, you have corrosion, you have byproducts, and you have irreversible hydrogen evolution. Okay. So in the electrolyte, we also have proton depletion, we have electrolyte consumption, and we have undesired CI chemistry. Somebody summarized these actually in this paper very nicely here. They have the Pourbaix diagram, and they have the set of reactions, the side reactions that happen in alkaline electrolyte and in neutral or mildly acidic electrolyte. So obviously you see that we prefer to work in mildly acidic electrolyte because the number of side reactions, at least in principle, is lower. So let me see in the chat here, there are, I thought, okay, we are good. So how do we deal with this problem? There, many people are going in different approaches. These are the problems in the middle right here. And at the corner are the approaches we are doing. So we are doing surface treatments. We are doing electrolyte engineering. We are doing substrate design. We are doing ionic transport and so forth. So what I'm going to do in the rest of this presentation, just give you 3 examples, one on the cathode, one on the anode, and one on the electrolyte of the strategies we have been studying to try to improve the performance of these batteries. So the first example is that we wanted to use 2D materials for zinc storage for the obvious reason that their structure is layered and also many of them are stable. So we started with molysulfide. But then, you know, what requirements you want from a 2D material? So it should have intrinsically large interlayer spacing to be able to accommodate the zinc. But let's say it doesn't. Some materials have other desirable properties. They are stable, they are cheap, they're abundant, they don't dissolve with electrolyte, but their interlayer spacing is not big enough. Actually, molysulfide is like that. So we need strategies to expand their interlayer spacing, maybe some electrostatic shielding, pre-intercalation, doping. Other strategies for the electrolyte, people actually use surface passivation or they use electrolyte additives. So the problem, as I mentioned, you are not intercalating only the zinc ion. You are intercalating a zinc ion, solvated by 6 water molecules. So you have a species here that's 5.4 angstrom in size. It means basically much bigger than the zinc, ion size. So let's see how the molysulfide, fares out with this. So if you look at molysulfide, actually the spacing between the layers is only 3.1 angstrom. Okay, so if you wanted to insert zinc, which is solvated by these water molecules into the molysulfide, it's a very difficult thing to do. First, you have to expend some energy to try to remove the water molecules. And what the question is that, what can we do to expand the spacing? It may be easier to leave the water around the zinc because actually this reduces electrostatic repulsion. So is there a way to expand the interlayer spacing in a reliable way for the zinc, the molysulfide, so we can intercalate the hydrated zinc? That was the question. So we did some calculation and then we found out just a 3 angstrom increase in the interlayer spacing of the molysulfide can allow you to intercalate 5 water molecules surrounding the zinc. So this will greatly facilitate the intercalation process. So how do you increase the spacing? There are different strategies. One strategy actually is to try to tune the hydrophilicity. Basically, change some of the sulfur atoms with oxygen. The oxygen, the oxygen when it goes into inside the molysulfide can actually intercalate. This is zinc, hydrogen, water around the zinc. This is the 6-fold coordinated zinc. When it goes in, if it finds oxygen, it can bond to it easier than to sulfur. So we call this hydrophobicity tuning. Tuning the hydrophobicity of the atom. So sulfur, molysulfide is hydrophobic, but molyoxide is more hydrophilic. So you replace some of the sulfur with oxygen, and then this becomes less hydrophobic. And what this does, it allows better intercalation. So we did a calculation also to prove this. Look at the blue and the pink. No matter the number of water molecules around the zinc, you will see when you have oxygen incorporated in the molysulfide, you will reduce the barrier to nucleation. And this drop along the y-axis, this just has to do, this is a calculation. If we increase the layer spacing, basically we are allowing more waters to be intercalated. And if you allow more water to be intercalated, because of this arrangement, then barrier for intercalation becomes low. So that was the strategy. Let's see how that affected the material. First of all, how to make this oxygen substituted molysulfide? Very simple, dihydrothermal synthesis. We pick, of course, we tried different chemicals, but this ammonium molybdate tetrahydrate, if you reacted with urea at 180 degrees C in an autoclave, you can actually form this oxygen substitute molysulfide. At 220 degrees C, you get only molysulfide. I will show you in a minute. Why is that? Because at lower temperature, the molybdate precursor actually does not completely decompose. So you retain some molybdenum oxygen bonds when you do 180. At 220, you don't retain many of these bonds. But because you retain these bonds, then when you react with the urea, then you can continue to have some of these bonds and you end up with the molysulfide oxygen substitute molysulfide. So we characterize this. First of all, if you look at the TEM and you look at compositional analysis, you see that this oxygen substitute molysulfide, in fact, has oxygen. Oxygen is in the blue here, and moly is here, and sulfur. Another thing you see that when you substitute the oxygen molysulfide, you see that the X-ray diffraction pattern is shifting to lower 2 theta. Means we have expanded the interlayer spacing. Basically, the moly-oxygen bonds actually weaken the van der Waals interaction between the molysulfide layer, and this allows you to expand the interlayer spacing actually. This weakening is also reflected in this shift in the Raman spectrum. You can also see in the TM at high resolution, this is the molysulfide by itself, 6.2 angstrom. But when you put the oxygen substitution, you end up with 9.5 angstrom. So all this data proves that oxygen incorporation into the molysulfide expands the interlayer spacing. Another thing is that you can also look at the XPS. Okay, we looked at the orbitals of moly3b and oxygen 1s. On top here is the molysulfide, on the bottom of molysulfide oxygen, and you can see this molybdenum oxygen bonding evolving with the oxygen substitution. You can calculate the exact composition after the hydrothermal analysis, and we find we have this position, 1.95 of sulfur and 0.05 of oxygen. There's another factor actually, it turns out, besides the oxygen and potentially crystal water. So if you do TGA analysis on these two materials, the oxygen substituted molysulfide and the molysulfide, you will see upon heating, look at this is the TGA here, the blue is the molysulfide. The X-ray diffraction pattern hardly shifts for the molysulfide when you lose this water. This is really mostly adsorbed water. But in the case of the oxygen substituted molysulfide, not only would they use adsorbed water, but there is some water that is lost at higher temperature. We believe this is called the tightly bound water. And you see that after you lose it, with the TGA, you have shift to higher 2 theta, means that we actually shrank the material. So then in summary, we believe this expansion in the interlayer spacing in the molysulfide by oxygen substitution mostly has to do with this oxygen effect about weakening the van der Waals forces, but we also may have a factor of some crystal water that remains. Also, there's a difference in hydrophobicity. So we know that molysulfide is hydrophobic. You can see the higher contact angle than oxygen substituted molysulfide. Now we have the material, and then we want to make the battery. So this is a battery we made. This is a first thing you look here at the A is the CV curves. You see that for the blue is the molysulfide. You hardly had any capacity because the interlayer spacing is small. The hydrated zinc cannot go in. But for the oxygen substituted molysulfide, you can see you have opened the CV curve, so there's substantially more capacity. The peaks in the discharge at 0.6 volt and the corresponding peak at 1 volt here, up here, and here. These correspond to basically intercalation, the zinc going into the molysulfide and coming out. This peak here at 1.34 is due to the change in the moly oxidation state. If you look at the charge discharge curve, okay, look at the pink. The capacity is about 200 milliamp hour per gram. And look at the blue, the capacity is under 40. Hardly any zinc goes in the molysulfide, but with this simple oxygen substitution, you can essentially have an order of magnitude increase in the capacity. This is reflected in rate performance. You see the pink here in C is actually recovering completely to the initial capacity after cycling at higher current. And then the blue one, which is molysulfide without oxygen substitution, has very low capacity. And this is the corresponding zinc diffusivity in the two materials, showing that substantially more mobile in the oxygen substituted molysulfide. So we looked even a little bit more in detail to look at the mechanism, what happens as the zinc goes in. So this is the molysulfide here after discharge. The word discharge here, for those who are not familiar, it means when the zinc goes into the molysulfide. That's called discharge in this arrangement. So in molysulfide, after discharge, the interlayer spacing is not changing. So that means no zinc is going in. But in oxygen substituted molysulfide, after discharge, we have gone from 9.5 to 10.7. This indicates that we have expanded the interlayer spacing because the zinc is going in, it needs a space. Another interesting thing happened actually during the intercalation of zinc. The hexagonal molysulfide transformed to 1T, which is the different form of molysulfide. And so that is a phase transition caused by the zinc intercalation. It turns out we're using this for other applications because this was not known before. People did this with lithium, but this was the first time we could see that by electrochemically intercalating zinc and molysulfide, you can do a phase transformation. The Raman here shows the molysulfide. This is the blue and the yellow, not changing at all after zinc intercalation because not much intercalates, but substantial changes in the pink are taking place because of the phase transformation. You look at the EDS, and you will see actually the sulfur, the zinc, and the moly and the oxygen. This shows that after discharge, again, discharge means the zinc going into the cathode, we have uniform zinc throughout. So that means we have successfully intercalated zinc in the electrode using the oxygen substituted molysulfide. You can, again, study in more detail and see what really happens. There's a lot of side reactions. So we did this. This is a very common experiment in battery analysis. You do a discharge and you do a charge. You make 6 or 7 or 8 batteries, and at different states of discharge, you take the battery and you analyze it. So here the pristine battery, and this is the battery after you discharge it. You see in the star here, we have formed the second phase. This phase actually is well known to form in this zinc ion battery. It's one of the headaches we have to deal with. It's a zinc sulfate, hydrate. So this hydroxysulfate, sometimes this phase forms right here. And then after charge, you recover, but you don't completely recover. Actually, it seems like some zinc stays in the cathode. If you look at the XPS, you get the same story. A down here, this is the fresh electrode. This is the fresh electrode. Upon discharge, again, discharge means the zinc goes in the molysulfide. Two things happen. First of all, you see the zinc in the molysulfide. That proves that we have intercalation. But also I have a peak which corresponds to zinc in this byproduct. This byproduct is not desirable. And you see here. Okay, let me just say one word about this byproduct. In general, actually, when we have these batteries, not only zinc intercalates, all aqueous batteries suffer from the fact that also protons from the electrolyte intercalate in the cathode. When that happens, you actually deplete the water near the electrode from proton, and it becomes hydroxyl rich. Therefore, the zinc reacts with hydroxide and forms the hydroxide and the sulfate, and it forms this phase. So this is actually on the anodes, the cathode side, a byproduct of the proton intercalation. So we have now a way, actually, you can estimate how much proton is intercalated here. The XPS is a little complicated, but it shows you the same story. Again, after intercalation, we have this 1T phase forming, and we have the oxidation state in moly oxide. And upon charge, you recover almost everything. So in summary, the mechanism here is a little complicated, actually. Zinc intercalates into the cathode. This is actually accompanied by the transformation of molysulfide into 1T phase. There's a precipitation dissolution of this zinc hydroxide byproduct. Luckily, on the cathode, this is a reversible process, but it may have detrimental effect on rate performance. And then we have a change in the oxidation state. So this is all I want to say about this example. So what is the take-home message? Take-home message that just a small amount, 5 atomic percent of oxygen substituting for sulfur in this material can largely expand the interlayer spacing and improves the hydrophilicity and allows the significant zinc intercalation compared to pure molysulfide. We have 3 orders of magnitude improvement in diffusivity and an order of magnitude improvement in capacity. And this strategy, actually, we have data can be applied to other 2D materials. So that's the first example. The second example, I want to go to the anode now. Okay, what problems we have at the anode? I explained earlier, we have zinc dendrite. We have corrosion of the zinc. We can also have hydrogen efflution and so forth. So one of the strategies is passivation, surface passivation with polymers, surface passivation with by alloying, surface passivation by different techniques. In this case, we used a sputter, titanium nitride layer. Titanium nitride is metallic, it's conductive, so we thought it would not degrade the overall conductivity of the anode. So let me tell you about the results of this experiment and how successful it was. So let me actually skip that slide. So here's what we did. You see a series of data here. We deposited titanium nitride by DC magnetron sputtering. It turns out, I knew this actually from background, that you can tune the orientation of the tinitride different ways. One of them is just to simply change the flow of nitrogen gas. And in fact, this is what happens. We have the pink here. This is a 200 oriented tinitride, and we have the yellow, which has mixed orientation, dominantly 111. What is different about these two materials is that in the 200 direction, actually the atoms lie flat, but in the 111 direction, they don't. There's some kinks. So there's some surface structure, and that was the idea, to try to see how this can affect the dendrite formation. And if you look at the Raman spectra, it matches with those of tinitride. There's a slight shift because of the structural orientation of the material. And if you look at the orbitals, titanium 2p and XPS, you see that they confirm that we have tinitride with the spin orbit splitting here. This material, if you look in the SEM, here is how it looks like, covering zinc. And if you actually zoom in and do some compositional analysis, you see the titanium and nitrogen here, and you see the zinc. So this confirms this is tinitride, and this is the zinc. You can zoom in and see its microstructure, and you will see that these different atomic arrangements results in different surface energies, and the contact angle on these two materials is different. So the first experiment we do is we do a symmetric cell performance to look at the cycling stability of the stripping and deposition process. So here you see three samples. You see the pink, which is the 200 oriented tinitride. You see the blue, which is 11 oriented tinitride, and you see the golden color, which is the bare zinc without the tinitride. Obviously, you can see that we can go to 2,300 hours of cycling. This is at a current density of 1 milliamp hour per meter square. In comparison, the two samples with the 111 tinitride and the bare zinc, they actually fail. And they fail by increasing the voltage. Given that this is a constant current measurement, this means that there's actually an increase in the resistor, not a short here. So this, we believe, is due to the product formation. This is EHS, which I will show you in a minute. You can go to different current densities. Okay, this is 1 milliamp. This is 2 milliamp, and this 5 milliamp, and you will get the same result. So this is substantial improvement by using the tinitride with the 200 orientation. Another thing, you see that you can do rate performance. Basically, you change the current density that you're passing through the cell, and you'll see that the tinitride continues to really perform well. And you see that the Coulombic efficiency of the tinitride, this is pink here, compared to the bare zinc, is substantially better. Actually, after a few cycles, nearly 100%. So to understand why this happens, we looked at the morphology. The first column here, A, shows you the bare zinc. With cycling, we basically have zinc flakes, these vertically oriented flakes that deposit on the zinc. And for one orientation, which is the second column right here, the same story. We have these vertically oriented flakes. But in the 200 tinitride, we actually have flat lying, these platelets. They lie flat instead of vertically. And you can go to 1,000 hours of cycling here, and you'll see they will still lay flat. And also, this results, if you look at the cycling, the sample after the cycling test, the initially pure zinc becomes corroded. This becomes dark. And this black, titanium nitride is conductor, so it's a dark color. So this black is the titanium nitride. After cycling, it also is corroded. And then the 200 tinitride remains actually intact after cycling. And so we looked at the elemental mapping at the samples, and we found out, especially for the bare zinc and the 1,1 titanium nitride, that we have this byproduct, ZHS, forming on the surface. Again, this is the sulfur, this is the zinc. That's a common byproduct if you, in this zinc battery. So we have to always find a way to get rid of it. So we analyzed this, for these different samples, the bare zinc, the tinitride 111, and the 200. There's in fact a formation for all of them, but the amount actually is different. So for example, if you look at the thickness, these pristine samples on the top. The tinitride, before we cycle the samples, is about 1.3 micron here, is about 1.4 micron here, the same thing. After you cycle, look, on the 111 tinitride, it becomes 4 micron thick. Okay, so there's a lot of byproduct is forming, and then in the case of zinc nitride, actually, in the case of zinc 200 tinitride, it has a thickness of 2.2, roughly half. So there's less of it is forming, and you can see that also in this chart here. This is X-ray diffraction pattern. Bare zinc is the blue, gold is the tinitride 1,1, and the pink is the 200. You look at that, and you look after 180 hours, the bare zinc has a lot of the second phase. The triangle, the green triangle, is the second phase. But look at the 200 zinc nitride. After 180 hours, actually, it has much less amount. So very clearly, the 200 tinitride suppresses that second phase formation. And this is another visual, illustration of the impact. Bare zinc, 111 tinitride, 200 tinitride. You see the thickness change as a result of this byproduct. It's significantly suppressed in the case of the 200 tinitride. This also, by the way, affects the EIS, and you see that the diffusion resistance, okay, which is from the intercept right here, actually after cycling, which is the solid curves, is smallest for this 200 tinitride. This is because it forms the smallest amount of this second phase. So how does this phase actually form? Basically, what we believe is here's what's happening. The zinc goes through this reaction, okay? This is during the solution process, form these two electrons. In the water, these two electrons are picked up and then form this hydroxyl. This hydroxyl can react with the zinc and the sulfate, and it can form this phase, okay? This, of course, leads to hydrogen. And if you look at the bare zinc, titanium 111 and 200 under the microscope and in situ, you will see that the bubbles are formed. This is evidence of the hydrogen reduction reaction. More importantly, if you look in the electrolyte, you will see that the electrolyte is being depleted of the protons for bare zinc, and then so that this is the pH is going up. That means there's more OH in the vicinity of the zinc, and this is the reason why we have this reaction. You can also see this visually on the electrode itself. This is after cycling for 48 hours. You see the bubbles here, but you don't see a little bit here, but you don't see in here for the 200 tinitride. So the story is very clear. This layer actually suppresses this second phase formation. And we made, therefore, some batteries to compare. In the interest of time, I would just say, okay, we see these CV curves for the two batteries. They nearly overlap, suggesting that the tinitride does not change the overall charge storage process. You see that the charge-discharge curve, they give you voltages that are consistent with this CV curve, okay? So as the zinc is intercalated, we have the change in the oxidation state of the manganese. You see that from the EIS spectra that actually we have the 200 tinitride actually has a smaller charge transfer resistance compared to the bare zinc. So all of this indicates that better performance for the 200 tinitride. Also, the rate capability test shows you this difference between the pink and the blue. And finally, the cycling test is not perfect for either of them, but basically it can go to 600 cycles. Incidentally, one of the things we also think in this battery is not only for like grid scale storage. One potential application is actually to replace the lead acid battery in conventional cars. And that lead acid battery, there are two features that it has. One, it runs at very high rates, but also it doesn't last very long with the number of cycles. So if we could get the zinc-ion battery to last 600 cycles, by the way, at a high rate, we could actually start thinking about replacing that because we are using much more benign materials, no lead and low sulfuric acid. So then to try to explain, let's see, I think I intentionally or unintentionally may have deleted the slide that shows the model. Actually, we did DFT simulations and we showed actually the root cause of this effect is that in fact, the growth of this phase DHS on the 200 direction or plates of the titanium nitride is energetically costly. Basically, it requires energy input. But to grow it on the 111 direction, because the atoms are not flat, if you recall, I showed you, actually the energy is negative. So the energetics of growing this second undesired phase on the 111 tinitride is actually favorable. So it's easier for it to grow. And that is the root cause of this thing. So by using this tinitride with the 200 surface orientation, which has the flat atoms, we basically lower the barrier for the nucleation of this phase on top of the tinitride. And that's why we produce such a good battery. So the final story here is that is about electrolyte engineering. So I gave you an example on the cathode engineering, and I gave you an example on the anode engineering. And this is an example about the electrolyte engineering. Okay, so one of the key problems here that is hydrogen evolution. We have a lot of protons in the system, so these water-related parasitic reactions must be suppressed, and people have been developing different strategies to try to suppress them. One strategy is called the water and salt electrolyte. Basically, you put a lot of salt in the water that disrupts the the hydrogen bonding network, and therefore the HER process. You can also have a co-solvent or what's called hybrid electrolytes to do the same thing. You can have additives, or you can engineer the interface so that it is more hydrophobic, for example. So let me give you one study that we did. We have a few, but this is one of them. So I think this study fits in the category of co-solvent. So propylene carbonate is one solvent. It's actually, if you look at it by itself, it's a nearly ideal solvent for batteries. It has a high dielectric constant. It means it can make the salts dissolve very quickly. It has high stability. It also has low viscosity. It means the ionic mobility is high and remains liquid over a wide range. It remains liquid from -48 to 242 C. So if you just look at it, this is really a very nice solvent. The problem is that none of the zinc salts dissolve in this material. So we have a lot of zinc salts. So you need to make an electrolyte, you need the solvent, you need the salt, and maybe you need additives. So the zinc salts don't dissolve in this material. And even worse, this material actually does not have good miscibility with water. You can only add about 17% by volume. After that, you get phase separation. So we were trying to actually engineer the electrolyte to see if we can use this material because it will allow us some desirable features. So what we discovered is that some molecules, a few of them, but this is the first one we discovered. This is the zinc triflate. Amazingly, what it does, this is the mixture of water and the PC, so propylene carbonate. I'll just say PC. It's easier. If you put this salt in this phase separated mixture, suddenly actually you can form a very nice and hybrid electrolyte. And that electrolyte actually is stable. It can be used in many different kinds of batteries. So let me dig deeper into this. So here's, for example, a group of vials. In the middle, you see water and PC, two solvent mixture. They are phase separated as you would be expected, okay? Especially as you add more than 17% PC. If you add zinc sulfate, a common salt for zinc, this phase separation on top here becomes worse. However, if you add zinc triflate, this phase separation disappears and you form very nice solutions. Even if you add 90% by volume PC, you still have a very clear solution. So this is surprising because zinc sulfate, like zinc sulfate, this zinc OTF is almost insoluble in PC. But suddenly you can dissolve it in 90% CV. So what is going on? So basically, we tried to see if this is unique to PC, but actually we found out this is universal. If you have other carbonates, ethylene carbonate, dimethyl carbonate, etc., you see when you mix them with water, they are phase separated. But you add this triflate to them, suddenly we form these very nice and homogeneous solutions. More importantly, also we found out the amount of salt that you need to add to achieve this miscibility depends on the size of this solvent molecules. It turns out it is proportional. The amount of salt is proportional to the solvent size because longer chains are more hydrophobic. So you need to add more salt. Okay. So we wanted to understand this more. We proposed one idea. Okay, why is this thing happening with this triflate? Well, what is different about this molecule is that if you compare it to zinc sulfate, the most commonly used salt in batteries, is that the zinc sulfate actually, the sulfate group is hydrophilic, but the OTF has two actually parts in the structure. If you look back here, right here, you see there's this CF3 part and this oxygen part. So we believe that these two parts actually, one of them is is hydrophobic, and the other one is hydrophilic. There's O3. So because of this, two ends on the molecule, it can actually coordinate with both the PC and the water. To prove this, we did many things. For example, one experiment, we took different salts of zinc. These are all sulfate, okay? And we started with, again, a mixture of PC and water that is not miscible. This is not miscible. And now you put these salts, they are conventional, like they don't, the solution remains immiscible, it doesn't mix. However, if you now add the triflate, lithium triflate and aluminum triflate, this is not zinc. These are different atoms, okay? Now you still can get a homogeneous solution. And more importantly, for lithium triflate, if you double the concentration of lithium triflate, you see the solution is even better. So that means definitely this OTF is the reason why we're having these homogeneous solutions. And also then we found out these other salts, they are more complex, but they have both hydrophilic and hydrophobic ends, just like the triflate. This is a different salt now. And amazingly, it does the same thing. So this really shows that if you have an anion that has two parts, one is hydrophobic, hydrophilic, essentially you can enable this homogeneous solution. Of course, we studied spectroscopically in more detail, and this is an example. I'll show you just a couple of examples. This is water right here, the blue, and you add PC to it all the way to 100% PC, and you see a peak. When you first have the triflate in water, there's no peaks here, but when you add PC, a peak starts showing up. This peak actually is a result of the interaction of the triflate with the PC. Similar here, you see there's a shift in the free OTF anions. That means when you introduce the PC, they are no longer free. They are interacting with the PC. You can look at the mother region, the SO bonding and the CF bonding, and you can see that also from water, you don't have these peaks, and then these peaks start evolving. And water, you have this peak here for CF, but this is becoming enhanced and bigger, okay? So this is also showing that we actually are interacting with the PC. Also, you can basically conclude that the solvation structure can be adjusted through the addition of PC to water in the presence of ETF. You can do this also with Raman. These are a series of Raman spectra for the same thing, looking at CS, SO3, and they all show, from nothing all the way the peaks developed as you add this PC and it shifts. So this is clearly, all this data collectively show that this anion is interacting with the PC. And we also did some Raman, NMR. You look at the oxygen 17 now in the water, and you see that as you add PC to the water, there's an upfield shift. Normally, this upfield shift means we have a shielding effect, basically putting more negative charge around this nucleus, okay? But this negative charge means we are disrupting the network, and we're putting OTF, which is negative, close to the water oxygen, okay? You also can look at the O17 in the OTF itself, and you see we actually have the opposite. We have a basically downfield shift. This is called the de-shielding, and this is basically a result of the fact that OTF may be coordinated with zinc, bringing positive charge around it, okay, and so forth. So all this data collectively basically shows the same trend. The OTF and the PC are coming closer around the zinc, and the water is being expelled. Okay, the water is being expelled, and they're coming out. I'm close to finishing here. We did some molecular dynamic simulations. In the first column here, you see water. This is OTF, zinc OTF in water, triflate in water. You see in the case of water, the zinc is fully coordinated with 6 waters, as we discussed before. As you add increasing amount of PC, you will see that the solvation shell is changing, and you see that the triflate anion and the polycarbonate start to coordinate with water. You can see here actually the pink here is dropping and the green is going up. The green is the PC interaction with zinc. And if you add 90% of this PC, you see basically the pink is dropped completely here, and then the coordination now is the green and the gray are actually the PC and the OTF group coordinating around the water. So this is proven also by the simulation. So we made the batteries, and again, one of the effects is actually this OTF, the PC addition increases the voltage at which you have oxygen evolution. It stabilizes the battery. Without this PC, look at the cycling performance of this battery. It's a disaster actually in aqueous electrolyte. But with the PC, you can stabilize it. You can also see the corrosion. This is a type plot. The increase in the potential along the x-axis, the drop in the current about the y-axis usually indicates better corrosion resistance. So by adding the PC, we made this more resistance to corrosion. And you can see that here, after cycling, what happens to the zinc when you use this salt in water and when you add PC. PC clearly stabilizes it. And the Coulombic efficiency is only 86 when you have water, but it goes up to 99.8 in 1 molar PC, and it goes to actually 99.93 saturated PC electrolyte. Look at the cycling performance. Similarly, with the PC, you can actually go to 1600 hours, which is really impressive. And what's neat about this solution, we have a concentration of about 2 molar. Water and salt, they use 15, 20 molar. It means you have to put a lot of salt, which is expensive. And on top of that, it kills the conductivity. So our conductivity here is 16 millisiemens per centimeter. But for salt, 30 molar salt in water and salt electrolyte is only 2.5. So this has an advantage with conductivity, advantage in cost. You can go to higher currents and you can still see the PC containing solvent is best. In the interest of time here, let me just jump to the end, we actually made full cell batteries, and we can very clearly see again the orange here is with the PC, without PC. Then you look at the Coulombic efficiency again with the PC and without PC. All along across the board, it has an advantage. And then also we are trying to work with these anode-free batteries. Anode-free batteries, why? Because there's 100 micron thick zinc. We only use, a fraction of it. This is really total waste. It also reduces the gravimetric energy density. So we use this cathode, and we use it with copper anode without any actually anode zinc. And we can make these batteries. These batteries still need a lot of work, I have to be honest. But look at the difference between the pink and the gray here. For anode free, this PC also gives you an advantage. You can see it here, and also with a 99.93 Coulombic efficiency. And you can also see the charge-discharge. So in summary, we have designed a hybrid electrolyte to suppress the side reaction with zinc-ion battery. This reduces the amount of free water, and it actually makes the electrolyte. I didn't discuss this, but the solid electrolyte layer interface is waterproof. So actually, this is good for reduction of the parasitic effects. And we demonstrated this with full cell batteries and anode-free batteries. And with that, I thank you for your attention.
Dr. Hassam, thank you very much for the nice presentation. I really appreciate it. I know that we have questions here. And if you have a question, and before that, please, I just put a form here in the chat. So once you have time, please just fill it. For the attendees. If you have a question, gentlemen, you can raise your hand and I will allow you to talk. In the meantime, there are 3 questions here, Dr. Hassam. Yes. So first of all, is about the lithium storage. So Al-Walid is asking, will the lithium storage run out eventually, in your opinion?
Yeah, I don't have the numbers in this presentation, but I will show you. We normally do this calculation. We have 3 billion cars in the world. If you want to make them all electric, you can't. So, as we make, more cars, and we don't recycle lithium, yes, we will not have enough lithium to make cars, let alone energy storage. With recycling, it is possible to mitigate some of this, but not completely. There will definitely come a time where we need alternate battery technologies. Other mobile ions.
That's why we need the different chemistries, including zinc-ion batteries.
Yes, zinc and sodium and potassium. These are all good chemicals.
Okay. Dr. Shahid, do you have a question? You can ask, please.
Assalamu alaikum, everyone.
Alaikum.
Yes, thank you so much for a very informative presentation. I have just one question, that if you compare aluminium with zinc batteries, you mentioned that volumetric density and gravimetric density of aluminium is higher than zinc. Other than this, the size of aluminium is also less, and aluminium is also cost-effective, and number of electrons involved in the redox reaction also higher. So what motivates you to focus on zinc instead of aluminium? Just
the oxidation of aluminum. Aluminum forms the oxides much easier than zinc, and that oxide has a band gap of 7 eV, which is extremely insulating. So you actually don't need a lot of oxide on the surface of aluminum to kill your device and then degrade its performance by a lot, actually. So that is the reason. However, having said that, there are people are trying to do this. For example, there are some studies coating different layers, ionic liquids on top of the aluminum, some surface engineering to mitigate the oxidation. But the problem is that thermodynamically, aluminum oxide is even more stable than SiO2. It just by all means, it wants to form, So if your coating is not really tight and any water gets to the aluminum, it's going to oxidize. That's really the main reason.
Oh, I got it. Thank you so much.
No problem.
Thank you very much. Okay, so Dr. Qasim is asking for the titanium nitride, how to prepare different orientations of titanium nitride? Is it only by changing the nitrogen flow? And also, did you investigate the effect of titanium nitride thickness as well on the performance?
Not much, to be honest with you, on the thickness, but let me make a comment on the physics of the sputtering process. Actually, there's different ways to control the orientation of a film grown by the sputtering process. Okay, the arrival rate, which is called the flux of the atoms, at the substrate, how fast they arrive, can actually control the orientation. If your flux rate arrives very slowly, the orientation you get will be the orientation that thermodynamics dictate. Basically, the lowest misfit with the substrate, lowest surface energy, and all of that. However, if your sputtering rate is very fast, and then the flux arrives at the substrate too fast, you are going to get a metastable situation, not the ideal situation. So you increase the flux by different ways, or you can reduce the flux by increasing the sputter power, by increasing the gas flow, because the gas flow will increase the pressure. There will be more scattering, so you can maybe slow down, the sputtering, the arrival rate of your sputtered flux. You can play with the pressure of the device. You can play with the substrate to target distance in the sputtering machine, and you can play with the temperature of your substrate. So this is kind of a conventional way of people how control not only the orientation, but also the microstructure of this sputter film, playing with these parameters. Gas was the easiest one for us to do.
Okay, thank you, Dr. Hussam. In relation to this question, Dr. Zahir is asking, should we consider other conductive nitrides, for example, aluminum nitride, chromium nitride? Do you anticipate to have different results based on changing instead of titanium to other metal nitrides?
Yeah, I think other nitrides in principle could do the same thing, but titanium is the cheapest. So if you go to chromium and you don't have toxic effects, you go to tantalum, and other exotic compounds, they are more expensive. So I think titanium is also good. Also, titanium is light. So
I see. Good. Thank you very much. Gentlemen, if you have a question, you can raise your hand. I will allow you to talk if you want to talk. Okay, so Sadim is asking, in the first example, you mentioned incorporating oxygen helps expand the interlayer spacing, which eventually help improve the zinc ion intercalation. However, would increasing the space be helpful for reversible process? Would it create a blockage, the material accompanying the oxygen? If the increase of oxygen is beneficial, correct me if I'm wrong, a material with higher oxygen, good affinity with zinc, and is based on the research. What is the best material to satisfy this requirement? I think the main question is, if you add more oxygen, it has more affinity to the zinc. So do you think if you add more oxygen, it will improve the reversibility of the process, or will it?
I mean, we played a little bit with the amount of oxygen, by the way, and I'm showing you the best data here. You don't want to oxidize it too much. This is for sure, because the conductivity also will change, you see. Polysulfide is not the only, and we did this, I normally present it, but you can only show so much. We also looked at a layered oxide like vanadium oxide, moly oxide, and I wanted to show this example to you because the difference was really more striking than we had anticipated. We did not really expect the difference to be an order of magnitude change in the capacity. It went from 25 to 250. But you could use oxides. We played a little bit with this. This was the optimal data we got.
Okay, thank you, Sam. Dr. Gandal, if you want to unmute yourself, if you have a question.
Dr. Sam, thank you very much for very informative and detailed physics, what you explained to us, mashallah.
Thank you, and it's very, very good to see you virtually.
Me too. Actually, I have same question what Qasim asked. I have same question first I want to ask, but you answered. Can we use a pulse laser deposition system instead of sputtering to control, because you said the flux and the speed both are very important. So with lasers, we can really give a very high speed in comparison to sputtering process. So can we use pulse laser deposition system also to control the orientation of TIN?
Yes, I think people do that. Yes, you can do for sure. The one disadvantage of there's advantage and disadvantage for the PLD. Okay, the PLD, the disadvantage, you know, is you could have a more defective film because it's inherently a more energetic process, right? But surely you will get the right orientation. And second of all, sputtering is more scalable. You know, I worked in the semiconductor industry. We sputter over 12-inch wafers, and they sputter on potato chips bags. They sputter the aluminum, but the PLD is not scalable. But from a scientific point of view, you can actually do a lot of creative stuff with PLD to study the fundamentals of
at lab scale.
Yeah, at lab scale.
But lasers are now using in industry. When you go to excimer laser, the beam you can expand and you can get little. I mean,
yeah, but not for growth. I meant I should qualify my statement. Of course, lasers are used in industry, but I meant for growth of films. You know, in the
semiconductor industry, they are using lasers as well now recently in Japan and other places.
Well, that's news to me. It is possible, but on 12-inch wafers, I doubt it.
Yeah, that's true. That's true. We agree with you. Thank you very much for
no problem. Thanks. Good to see you.
Nice talking with you. Nice talking with you.
Same here.
Thank you. Okay, we have a lot of questions, Dr. Hussam, and I know that we are limiting ourselves to 1 hour. So maybe I will conclude with one question. So it's from Dr. Sayed. So thank you, Professor Hisham, for excellent talk. I would like to talk about the stability of the electrolyte under higher environmental condition, under higher operating potential window. What is the best strategy to overcome the electrolyte decomposition? Also, I would like to know about the commercialization of electrochemical capacitor. This is beyond the scope presentation, but that's fine. So where would we see the supercapacitor in the next 10 years, and whether they will be they will compete batteries? So first of all, I think about the stability of in terms of temperature, in terms of the potential window, how to increase it. Yeah, go ahead.
Yeah, I mean, we study all of these. I mean, you saw actually in the example I showed, in these, you know, these are aqueous systems. So we have to be honest with ourselves and set our expectations correctly. You know, in the conventional battery, lithium-ion battery is a 3.7 volt and maybe higher battery. These batteries, you know, theoretically the water, you know, you cannot use above 1.23 you know, volt. However, you know, some electrode materials, they have poor catalytic activity, you know, and you know, for example, we studied magnesium containing compounds. You could expand the voltage window by choosing materials that don't have electrolytic activity, but also more importantly, you can disrupt the hydrogen bonding network in the body of the electrolyte. By example, like the strategy I showed by introducing PC. These are the strategies people use to increase the voltage. You could also choose a cathode that intrinsically has a higher voltage, like manganese oxide, for example, cerium oxide. So all these strategies you can go after, okay? And your second part of the question about the supercapacitors. So the context of this talk is grid scale storage or capacitors are not going to be used for grid level energy storage. That's not what they are used for. Capacitors, there are their own markets. There are the conventional markets, which have to do with, you know, power tools, regenerative braking systems. You know, they can help actually electric cars. All the Teslas have this capacitive energy storage on them. Cranes, you know, doors of, you know, planes, you know, power interrupts, UPS systems. The capacitors will continue to be in this space. But a new space that actually my group is very active in for capacitors is self-powered sensors. You know, people here at Chaos, they are all working on these Internet of Things, sensor networks, healthcare Internet of Things. And there, you know, people are thinking about billions and billions of sensors. And the idea of changing their batteries every year, nobody's going to do that. So there's a big push, you know, to utilize vibrations or temperature to just generate small amount of energy and store it for, let's say, you know, not continuous use, but we'll say standby use. So for example, a sensor will wake up 2 or 3 times a day, do a measurement and transmit a signal. So the supercapacitors are ideal actually to integrate on these these are called micro supercapacitors, we call them. These are ideal. And in fact, we have integrated them with transistor, with electronics. This is another application. It could be big. It's also the on-chip frequency filtering. These are the capacitors. They don't really completely compete with batteries. Some hybrid capacitors, Professor Atif Zahrani talked about hybrid capacitors. I know for lights, night lights, for example, in some countries, they have solar panel, and they store the energy in a hybrid capacitor during the day, and at night they light the light not from a battery but a hybrid capacitor. A hybrid capacitor using lithium titanate, for example, and a carbon. This is an intermediate energy density. It can power these at night, and it can last significantly longer than a battery. So hybrid capacitors could probably in some markets eat the battery, but the capacitors, maybe in buses that make frequent stops, maybe in power interrupt systems. These are the regenerative braking, but to imagine grid level storage for a city with capacitors, I don't think so. I lost you.
Thank you. A final question from Osama Al-Harbi. He's a student. Osama, do you have a question?
Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you for your really informative webinar, and thank you for the organization of Dr. Atif. My question is it a good strategy to use zinc ion for electric vehicles, or only suitable for stationary applications? Thank you.
Yeah, the energy density of the zinc ion battery, the rechargeable zinc ion battery here, is actually quite a bit lower than that of the lithium ion battery. So to be honest, is that this really would not be the biggest market where I would anticipate it will go. Although, the theoretical values for energy density are high, and if one talks about zinc air batteries, we could actually, if we succeed, or zinc reflow batteries, we could succeed with some of the zinc air and the rechargeable batteries that use different cathode materials could succeed. But my prediction, my humble opinion, is that this is a technology that it will, if it succeed, it will first succeed in the grid scale energy storage, not in automobiles.
Okay. There are lots of questions, Dr. Hassan, but I don't want to keep you anymore.
No problem.
Thank you very much, Dr. Hassan, for your presentation. Thank you for the attendees for attending and for the informative discussions and questions. Dr. Hassan, again, I reiterate my appreciation to you and for your time. And hopefully we'll be in touch, inshallah ta'ala. Thank you.
It was my pleasure. Thank you, everybody. Thank you very much for the invitation, and thank you for the audience.
Thank you.